Okay, the content of my lecture will be Levi form. Levi form of a real hypersurface. Properties. And then example and exercise. Okay, so let's come back a little bit what we did yesterday. So we start with Z. The coordinates will be always in Cn cross C. And M will be always given by locally by MW is phi, where phi is a smooth real valued function of Z, Z bar, real W, with phi of 0 is equal to 0 and d phi of 0 is equal to 0. It's always possible after holomorphic change of coordinates to get that in Cn. So we leave in, instead of capital N, it's n plus 1. Okay? And I recalled nu will in CTM, so we complexify the bundle of complex tangent bundle. It's going to be it's a CR bundle. Force fiber is exactly what we saw yesterday. Force fiber at P. You remember nu P was what? The holomorphic, the anti-holomorphic vector field, that is L is, it's a set L of CG D ZG bar. Okay? And you can look also at vector field, CR vector field, where you let the coefficient, it's like a smooth section of the CR bundle. So it's going to be given by L is summation Cj of P. This is smooth function. This is not holomorphic function. So I should say Cp P bar d Zj bar at P. So this is a smooth section of the CR bundle. Nu force fiber is nu P. It's a CR bundle because the nu P has always the same dimension. Remember, the dimension is little n. Dimension of nu P is n. And as I said yesterday, when you go to codimension bigger than 1, then you have to be careful because it's no longer a CR bundle. Okay. Any question? So this is smooth function. There is nothing with holomorphic. Smooth function. P is in N. Okay? Now, a basis, you can just look for a basis of CR vector field. It's very easy. They are given by Lj is dzj bar minus 2i. If I take this setting, M, minus 2i phi zj bar over 1 plus I phi s dw bar. They are given by that. You can check it easily. Ng goes from 1 to n. It's a basis. It's clear. Okay? So you have a basis of CR vector field. And I would like you to do the following exercise because you need a parametrization. You always work in the parametrization. Look, if you take, this is an exercise. If you consider psi, z bar s goes to z s plus I phi z z bar s. This is a parametrization. This, and you can check the push forward by psi minus 1 of this Lj is given by lambda j is d dzj bar minus I, it was a 2I here, but now it's minus I, phi zj bar over 1 plus I phi s dds. There is no longer dw bar. Minus 2I, this is the same, but it's minus 1 ddds. So the push for, if you look at this CR vector field in the parametrization, they look like that. And usually you work with this form. So it's an exercise. We will discuss maybe this afternoon. Okay, it's all I wanted to say about the basis. And now we will go to the Levi form of a real hypersurface. So, nu p, remember, this is a fiber. This is then TP01Cn, which is the anti-holomorphic vector field in Cn, intersect with CTPn. You can look at that like that. So Lj, I still write it's ddz bar minus 2I phi zj bar over 1 plus I phi s ddw bar. Now, let's consider the following projection. You take CTPM, the complexify tangent space, and you go to CTPM mod out by nu p direct sum with the conjugate of nu p. Anti-holomorphic and holomorphic one. Okay? What is the dimension of this guy? This is n, and so it's 1. In the real hypersurface case, this is 1. So, and you consider the following map. First of all, a comment before going. Remark, important remark. If x and y are CR vector field, that means with smooth coefficient depending on p on m, tangent on m, defined near p, with x of p, let's say it's x, you write x of p is xp, and y of p is yp, then if you consider this is a projection, I didn't say, this is a projection, okay? If you, projection map, then this guy, the projection of the bracket, okay, at P, you consider this guy. The bracket is still in CTPM. If you have two vector fields, the bracket is still there, okay? if you consider this guy, you know, what? It's a Lie bracket. Yeah. So you could have lots of x such that x of p is it's not unique. But this guy depends only on the value xp and yp, and not on the vector field you choose. You know, they could be different. You could have two vector fields with the same value at p. But if you consider that, it's just depend on the value of xp and yp. Okay? So it's an exercise. It's not hard. When you bond out, there is no problem. Therefore, you can make a definition which makes sense. And the following definition will be the following. Where is my definition? Definition. As soon as you check that, you can make the following definition. The Levi form, called also the Levi map, because here I show in the real hypersurface case, but you can do the same with codimension bigger than 1. So it's going to be the Levi map, also Levi map, in more general context. Is the Hermitian form given by LP goes from nu p cos nu p over c t pm over nu p plus nu p, direct sum with nu p, and to x, the value at p, you really xp up, you send to 1 over 2i projection pp of x, y at p, since it's well defined, because it depends only on the value xp and yp. 1 over 2i projection of the Lie bracket. Should I define again the Lie bracket, or everybody knows what it means? Yeah. Thank you. There is I will do better. So here it's.
Marker, please, because the black is very hard to see now.
Sorry.
Can you choose a new marker? Yes. New one. Yes. New one.
Are they new or just recycled? Okay, so you take the Lie bracket, x, y bar, I forgot a bar, but you see that there was a bar here, okay? And you evaluate at p, this guy. P, yeah. Everybody knows what the Lie bracket is? Yes? I should define. So x, y, applied to rho, is x, y rho minus y, x of rho. So you see that it's, if rho is a defining function and x and y are complex tangent vector space, this is a tangent space, vector space, okay? Okay, you can wonder why to divide by 2i. It's to get a Hermitian form. So maybe I should show that it's a Hermitian form. just to. And when it's a Hermitian form because the dimension is a real hypersurface case, it's 1. So how do you show that? Just for it's an easy exercise, but I'm going to do since people maybe don't. So what do you have to show? The Levi form, the Levi map is a Hermitian form.
We do see Levi form, not Levi map. You say.
Levi map is when you have codimension bigger than 1. Just to say that the definition, there is a more generalized definition, but I'm talking only on a hypersurface case. But you can mimic and have the same if it's a CR bundle. I mean, it's not always a CR bundle, so you have to take CR manifold in order to do this kind of stuff. So Levi map is a Hermitian form. So you have to show, if I write this, I have to show x plus byz is ax. That's clear, I think, because plus byz, I guess it's clear because, this is linear, okay? The only problem is what happens. So for me, x, when I say x, y, it means 1 over 2i. What is it? Okay, I'm using this this notation. So there is no problem to see that because there is no problem with the linearity. The only problem is to show that yx is x y bar. Okay? But it's easy because you have an I. So, and because of the bracket, just let me show that just. So what does it mean? So you have to what is yp xp? By definition, it's 1 over 2i yp xp bar, right? And xp, yp, it's 1 over 2i xp yp. That means that xp yp bar is minus 1 over 2i. And what is the bar of this guy? It's going to be x bar py, okay? Okay? Yes? And now, boom. So it's going to be minus sign is going to be 1 over 2i yp xp bar, and you look up, and it's the same. Okay? That's why you put an I, to get a Hermitian form. Okay?
There should be the projection, but it doesn't change anything with the...
Yeah. So, sorry. Yeah. It's a projection. Yeah. Sorry, but it's the same. Because you remove the term, but it's the same, even though, yeah, exactly. Okay. So, how do you recognize the Levi form? So an example. I give you in its C2, let M be in C2. It's nice, you have just two variables, Z and W, Z, W, and you give yourself M, it's ImW equal to, let's say, 2 ZZ bar plus Z square, Z bar square, plus, let be like that. And I would like to compute the Levi form at 0. What is the Levi form of M at P is equal to 0? What is your guess? Can you directly tell me what it is? 2. Who said that? Good. Do you know how to do? Yeah, you have to compute, but after a while, there is an algorithm, and you see, you have the first ZZ bar. It's my first term. Yeah, you have to be. I'm sorry. You are maybe used to write in X and Y real coordinate. That's why now we work with the ZZ bar coordinate. So you write like that, which means 2. You know, it's 2. X squared plus Y squared, if you want to be real. But and in fact, the Levi form at 0, you only have to consider the term in ZZ bar when you are in C2. It's exactly these two. So let's compute it. How do you do? You have to be in nu P. You remember it's a map which goes from nu P, the CR vector field. I gave you the basis because it's only on how many bases? What is the dimension of the basis in C2 for nu? Just 1. I gave you the form. It's L is given by what? There is just one J. So it's ddz bar minus 2I. Let's say in the parametrization. So it's minus I. Then you have phi z bar. This is phi, okay? I don't want to, I want to be lazy. And there is no real W. I just took something very easy over 1 because there is no real W. So the 1 plus I phi s, there is nothing here. So it's just like that, dds. And it's enough for a Hermitian form to compute on the basis, right? So we have only to compute. What? DDS? DDW, remember, but now I am in the parametrization. It's the same, but like that. It's okay? And it's just 1 plus I times 0. Now, what is L bar? What is L bar? So I have L ddz bar minus I phi z bar dds. So what is L bar? I need L bar. What is L bar? It's ddz, okay? Plus phi is real, so it's I phi z, because phi is real. Yeah. Okay? So plus I phi z, and dds is dds. It's real. Okay? So I have to compute the projection, but I will just compute LL bar. 1 over 2I, okay? Projection, but let's forget about the projection. There is no coefficient, there is no problem. So I have to compute ddz bar minus I phi z bar dds, okay? I'm going to do that because I'm not sure you are used to this kind of ddz plus I phi z dds. Let's do it. No contribution. Where is the first contribution coming? What is the result of that? Nothing here. Okay? You agree, or you are not familiar with that? You agree that there is nothing here? Because it's ddz. If you interchange the derivative, nothing happens. The trouble starts with this guy. Okay? Because ddz bar, you have to apply ddz bar to this guy. Okay? So it's going to be what? It's going to be I phi zz bar. You see? Zz bar. It's exactly the first zz bar dds. You agree? And now you have, if you go like that, no trouble. The only trouble will be, no, there is more term. I should be, there is a term here. Don't forget this one. What is the term? You have to apply that to that. But we have no problem here. Why? Because there is no s. So I don't have to, if phi was carrying a s, I will be in trouble. But I can forget about that. And now you have to go like that. ddz bar, there is no problem. And what is the term here? It's a minus what? Because when you have the skew, so it's going to be what? You have to apply this guy, it's this guy, to this guy. And it's going to be what? Minus, so it's plus I phi, and again, z bar, z bar, you don't see the difference. So it's going to be what? Plus I phi z bar dds. Okay? And I have a 1 over 2i. And I want that at 0. Okay? So it's going to be phi z bar at 0, because I'm looking at. So what is the only term which matters when I go to 0? Look, if I differentiate this guy, it's going to be 1, it's going to be 2, and the rest disappear because it's of higher order. At 0, it's going to be 0, the rest. So I get exactly these two. You see? So when I give you, even though now you can check, because now that you know that d phi of 0 was 0, this is very important when you compute it. See, if I had put plus, if I had changed a little bit and putting some s here, does it change or not? Say even like that. Say that. At 0, what do you think? It's going to be the same. Why? Because you have phi z bar dds, and phi z bar, it's at 0, it's 0, because you choose a good system of coordinates. Okay? So at 0, you see exactly. For C2, you have just one eigenvalue. It's just, the matrix is just it's a number. Now you can guess, now that you understand how it goes, if I jump to Cn, or to C, what happens? By the way, you remember yesterday I told you that there was a model, this, I was talking about the Levi hypersurface. It's one, the Levi number. Okay, if I take, if I take in Cn plus 1 im W and then I don't know, I have A11 Z1 bar plus A12 Z1 Z2 bar plus AN Z1 Zn bar. Since it's real, I have all the possibility, okay, plus, etc., plus higher order term. Okay? I consider only the term in Z I, Zj bar. Okay? So I can write like im W is summation Aij Zi Zj bar plus higher order term. Since phi is real, that means what on the coefficient? Phi is real. So you have Aij is what? Okay? And in the light of what we did for C2, where is the Levi, where is the Levi form? What is the Levi form? It's given by what? The matrices Aij. So it's a matrices now, which is it's real. So the matrices Aij, it's the matrices of the Levi form at 0, at 0. And if you consider coordinates where the gradient at 0 is 0, okay? So you do the same. You have to compute, instead of L bar, you have a lot of them. You have to do L, but it's the same. Because when you apply Li, Lj bar, it's going to be phi Z I, Zj bar. So you hit every coefficient here, okay? So now, I have this Levi form. And now I want to say what a pseudo-convex hypersurface is, or a Levi non-degenerate hypersurface is, because it's going to be a crucial point when we will be study biholomorphic map. The Levi non-degenerate case will be the key case, and I think the model case to look at. So we have to understand very well what it means. So now that you believe that it's a Hermitian form, we can talk about Levi non-degenerate Levi form. Oh. So what is the definition of a Levi non-degenerate hypersurface? Definition. The Levi form is not degenerate if the Levi form is like that. Every time you have that, for every yp in nu p, what is the conclusion is that xp is 0. It's a usual way of a non-degenerate form. Okay? That means that the determinant of this guy has to be how? At 0? Non-zero. Non-zero. If it's non-degenerate, at 0. Okay? At p, because you can look at p, but now I'm going to say at p is equal to 0. So example, and m is said. Oh, maybe not yet. Okay, example. If I give you im w equals z1 bar plus s z1 plus s Z1 bar plus Z2 bar. What?
The matrix
Yeah.
is the identity?
What is the matrices?
The identity.
Yeah, it's going to be 1, 0, 0, 1 at 0. So it's Levi non-degenerate. Okay? Now, if I give you in C3, but in C4 no longer, okay? Now, if I give you in C2, MW is Z square, Z bar square. What's going to be? It's Levi degenerate. Because if you compute it, there is nothing at 0. Okay? So now, we have to, what does it mean to be pseudo-convex? Definition. M is pseudo-convex. M now at 0 if the Levi form is either positive, semi-definite, at all p in a neighborhood of 0, because it's not an open condition. You need in a neighborhood of 0 or negative semi-definite at all p in such a neighborhood. You want to have that for all p in a neighborhood, because if you give yourself at 0, it's not enough, because it could be 0 and then it's not an open condition. So it's a pseudo-convexity. Can you give me, is this one, for instance, in C2, what do you think about this one? Is it pseudo-convex at 0 or not?
No.
Yes? At 0, it's Levi non-degenerate, but it's 0 or bigger or equal to 0. But what does it mean? You have to be positive semi-definite. That means that the matrices is big, the determinant is bigger or equal to 0 at even. So you can check that it's okay for this one. But at 0, it's not Levi non-degenerate. So this is pseudo-convex. But not strictly. It's pseudo-convex. Now, similarly, we can define what is a strictly pseudo-convex. What is strictly pseudo-convex? It's definite positive, okay? It's not semi-definite, but it's definite positive. So M is strictly pseudo-convex.
See, it's probably time for a new pen.
Thank you. at 0, but you still read it. Oh, yeah. Okay? If what? It's only, you only need to know what happens in 0, because if it's bigger than 0 at the origin, then it's an open condition. Okay? If the Levi form is positive or negative, definite, okay? That means that you have real eigenvalue positive or negative, strictly positive or strictly negative, okay? So, just a few examples, because it's very important for the rest of the lecture what it means. So let's consider C3, and I will give you a bunch of stuff. For instance, no, in C2 first. If I have, in C2 I have only, it's a number. So if it's Levi non-degenerate, looks like how? If, say in C2, if you have a Levi non-degenerate hypersurface, how does it start? What is the first coefficient in the power series of phi? Exactly. Plus higher order term, because there is no z bar, because you decided that you have. And what is the number? The Levi form is given by what here, the number? It's going to be precisely this A. So when you are Levi non-degenerate in C2, you are always strictly pseudo-convex, right? A is real also, because you are in a real, phi is a real function, it's a real hypersurface. Okay, so it's always Levi non-degenerate. In C2 implies it's always strictly pseudo-convex. Fun start with, C3. So I will give you some, and you will give me some ideas. So if I give you this guy, I will give you, in C3, MW, or plus higher order, I don't know, plus, let's, Z2. Then I give you this one. I will just give you one. I prefer that. And I will give you also MW is Z1 bar square plus Z2 square. And finally, everything is here. Okay.
This is in C3.
This is in C3.
Oh, it's a 3, is it? Sorry.
Yeah. It's, oh, sorry.
No, that's all right, that's all right, that's all right. Yes.
So I have 3 choices. Can you tell me which one? Are they all non-degenerate? Is there something which is missing or not? If I take the first one, you see Z1 bar square plus Z1 4, Z1 bar 4. This is perfectly legal because it's real, no problem. Is it Levi non-degenerate? What is the matrices, I mean? What is the matrix of the Levi non-degenerate? If I take this one at 0, what is the matrices?
1, 0. 1, 0, 0.
Ah. Yeah. So it's 1, 0, 0, 0. So the answer is? It's Levi.
Positive, but
It's Levi degenerate,
positive.
and it's pseudo-convex.
Yes. Not strictly.
No. Because it's Levi. So it's Levi degenerate and pseudo-convex. Okay. Then, if I take this guy, what is the matrices?
1 minus 1 in diagonal.
So it's Levi non-degenerate, but you have two eigenvalues of different sides, so it's not pseudo-convex. Okay, you see? And finally, if I take this guy, it's strictly pseudo-convex. And if I put that, even though it's the same, I can put minus, minus. Okay? So, what is the time? Do I have a little time left? Yeah, good. So I would like to go back to maybe to the exercise that the LJ, the form of LJ. Since I gave, yeah. So the basis LJ d dZj bar, I told you that minus 2i phi zj bar over 1 plus I phi s dw v bar. Why is it a CR vector field? Somebody wants to do it? Just the computation. So I remember that M is given by IMW is phi of z bar real W, which is S. I can put real W. If somebody is willing to come, it will be great, so we can make a little exercise during the end of the lecture. And I would like you to prove that LG is a CR field on M. It's easy, but just there is few minutes left. Thank you. Yeah? Who is coming? Yes? You? Nobody wants to try? I'm sure you can. So how do you do then? We will finish that like that. How do you do? What do you have to show? What?
Or it kills the...
Yeah, so how do...
Oh, I don't want to.
Okay, so tell me what to do in order I can be sure that everybody has understood what I have to do. So, what is I have to apply LJ to what? To what? To this guy. So what is the defining function? W minus W var over 2i. This is IMW minus phi of z bar. Okay. So let's go. And I have to, is it 0? Come on. So I apply d dZj bar minus 2i phi zj bar 1 plus I phi s ddw bar to this guy. What is the first term? d dZj bar, there is nothing to do here. So it's going to be what? Minus phi zj bar, okay, of this guy. And then here, what is that? Minus 2i, and then phi Cj bar over 1 plus I phi s, and then what is the derivative with respect to this guy? Times minus 1 over 2i, and then it's Leibniz rule. So what do I do? Minus phi s times the integral derivative, which is what? 1 over?
1 over 2.
Yes. Okay? Yeah. And then I guess it's clear because what is this one? This is minus 1 over 2i. If I multiply by I, it's minus I over 2i. Is it correct? Yes? Phi s. Yes? Yeah. And now you are leave. This 2i doesn't exist anymore. And now what? It's going to cancel.
1 plus.
This is upstairs, this is downstairs. There is a minus. Minus, minus, plus. And I have a minus here, and that's it. Okay? But now it's a little more challenging to see what happened in the parametrization. Because when you go to the parametrization, you replace ddw bar by dds. And it becomes minus I. And there is it's just a question of differentiation. But I think it's important to understand how it goes. Otherwise, you never. OK, so I don't want to. I think I'm going to leave. It's fantastic. It's before the lunch.